Hello, everyone. My capstone project was to explore patterns between soil moisture and rainfall during landslide events in the Western US using satellite observations, and my mentor is Elsa Culler. So landslides matter. They are a serious geologic hazard common to many areas in the US and Canada. There are negative economic, transportation, and habitat impacts resulting from landslides. And there are climate change implications where drought or heavier rains affect the number and severity of landslides. My approach is to use satellite measurements of soil moisture as a proxy for rainfall-induced landslides to examine the agreement or disagreement between soil moisture and precipitation, to look at soil moisture levels that trigger landslides and correlate what I see with soil type and saturation levels, and to compare results among sites. The end goal are Jupyter notebooks, one which assembles all data on a common data frame indexed by landslide ID. Another is a notebook that generates plots and statistics for analysis and interpretation. And these notebooks can be run for any US state affected by landslides. The study area is primarily Colorado. The landslide data come from the Global Landslide Catalog. The time period is 2015 to 2020. Unfortunately, I cannot go back in time and include more landslides in the past because I'm constrained by the time periods of the satellite data that I'm using. So here I'm showing a map that plots all the landslides within that time period, color-coded by trigger. However, this analysis can be applied to any US state where the landslide catalog archives events. For example, if you want to compare and contrast, which is what I'll show in my results slides coming up. So in my results slide 1, here I'm showing a scatter plot of total rainfall accumulation for a week prior to a landslide event on the y-axis from the NASA GPM satellite instrument versus the maximum soil moisture within a week prior to the same landslide event on the x-axis. And these data come from the NASA SMAP instrument. I observe a linear relationship between soil moisture and precipitation for Colorado, meaning there's a good correlation of soil moisture responding to increasing precipitation. However, the type of landslide, color-coded and based on the Global Landslide Catalog, seems randomly distributed or not descriptive at all. Like they have a category called landslide, which are the yellow circles, which provides no detail whatsoever when one considers that there are half a dozen to 10 types of landslides out there. So this is a real limitation of using the Global Landslide Catalog metadata when identifying landslide types and rainfall triggers. So is this linear relationship unique? So here I'm showing Colorado on the left with Oregon on the right, landslides over Oregon on the right for the same time period, which is a region that gets a lot of rainfall. So you can see in Oregon, it looks like the data form a triangle. The hypotenuse side of the triangle shows a strong linear relationship where soil moisture responds to precipitation amount, like what you see in the Colorado plot. However, the rest of the data shows that it doesn't matter how much rain falls. The ground is saturated such that the soil is invariant to precipitation amounts. And I have found this pattern, this triangular pattern, true for all coastal sites. Inland, there's so little data outside Colorado, it might as well be considered a unique pattern. So it makes sense to look at what the soil types are. And Elsa suggested I would find these in the Polaris 30-meter probabilistic soil properties TIFF images. The top plot shows the KSAT values for all rainfall triggered landslides in Colorado. And KSAT is a measure of how well or how easily water can pass through soil or rock. From what I've read, a KSAT greater than 0 indicates saturated flow. And you can see from this plot, most landslides occurred in saturated soil conditions. The plot below is the percent of sand, silt, or clay for each landslide. And sand or gravel wins out, which are these green circles. And again, from what I've read, that percent combination of 40% sand, 30% silt, and 20% clay can have moderately high runoff potential when thoroughly wet. So runoff rather than infiltration-driven events are the dominant physical mechanism for these landslides. And this is my final slide. Unlike coastal states, where the water table tends to be saturated, soil moisture in Colorado responds to changes in precipitation in a somewhat linear way. From my analysis, this pattern is unique. From looking at soil types, the runoff-driven events are the dominant physical mechanism of these Colorado landslides. The type of landslide seems randomly distributed and uninformative, indicating limitations in identifying different landslide categories. The global landslide category metadata is not particularly accurate, and this further complicates determining rainfall conditions and types of landslide disturbances. Personally, I would ignore the GLC. I would ignore the GLC categories and triggers and create your own using satellite tracers and model reproducibility based on known hydrological processes. And furthermore, the GLC doesn't capture all landslides, particularly after 2018. There's a severe tailing off of the number of events cataloged as if the curators abandoned the project. So in terms of next steps, Elsa and I talked about k-mean clustering to identify different hydrologic and soil signatures that can cause landslides, and that would probably be the next step. Otherwise, to be perfectly frank, this is a heavily research-based project where the end result would be a peer-reviewed paper. So this implies that I have some level of landslide knowledge and expertise, which I do not have. Thus, I would hand off the notebooks to Elsa for her ongoing research and colleagues. So thank you for your time. Thank you, Elsa. You've provided excellent guidance and mentoring just at the level that I needed.